fine. You can see all my imperfections. Ready?
Okay. Right. So, with that, okay.
Okay. So, I'm going to talk about inverse Turán problems. This was joint work with Erwin Dury, Nika Salia, and Asker Zamora. So, as usual, let me start by introducing some normal Turán problems and explaining how that works, and then I'll talk about this variant. So, the classical extremal number, Ex and F, for a fixed graph F, is defined to be the maximum. So these are complete bipartite graphs between the classes. And okay, if you calculate how big is this number, this is equal to t minus 1, choose 2, choose the two parts, times n over t minus 1, quantity squared, right? Which is in turn equal to 1/2 times t minus 2 over t minus 1 and squared. So this is Turán's theorem. And so before I get into the main topic, I want to recall some things in the classical Turán theory because we're going to use those in the results. So what's the first natural generalization of this is, what if instead of the complete graph, we consider some other three-chromatic graph? So it was proved by Erdős, and Szymonovich that for any three-chromatic graph, so if chromatic number of F is at least 3, then Ex and F is, well, asymptotically equal to the size of the Turán graph, but instead of a t, we put the chromatic number of F. So it behaves like the clique with the chromatic number F, number of vertices. Okay. So this was due to Erdős and Szymonovich. And also, there's a so-called color critical theorem of Szymonovich that says that actually, if F is a graph such that there's one edge in F that we can delete that will reduce its chromatic number, then in fact this is not just asymptotic, but it's actually equal. So it behaves exactly like the clique. So I'll just mention that, I won't write it. Let's see, what else? Okay, let me also mention the theorem of Kövare, Sós, and Turán. So if instead of, so basically this Erdős-Szymonovich theorem settles the Turán problem in the three-chromatic case, I mean asymptotically for any graph F, but the bipartite case is still difficult and there's many open questions. So in the bipartite case, of course, the natural question is, what about the complete bipartite graph? So in this case, Kövare, Sós, and Turán proved that Ex and KST. So this is the complete bipartite graph with one part size S and the other T, all the edges between them. This number is upper bounded by a power of n, which is something like n to the 2 minus 1 over s. So to get the best bound, we might as well take s to be the smaller side. So we can always say that this is true. So most number of edges we can have with the KST free graph is something like n to the 2 minus 1 over s. And in some cases, this is known to be sharp. So for instance, so for K333, this is known to be sharp by construction of Brown. And some other cases, I guess if T is at least S factorial, This was proved by, who was the first author of it? Yeah, by Kolar, Ronyai, and Sabo. And this was later improved to, instead of saying t at least s factorial, we can even say t just has to be s minus 1 factorial. And it's also proved that this is sharp by Milan, by Sabo. So this seems to be the right order of magnitude, but it's still not solved for all k st. Okay, so that's about complete graphs. The next natural case is cycles. So there's a theorem of Bondi and Shimonovich. Which says that for any cycle of length 2t, right? So the odd cycles are 3 chromatic, so we know their Turán number asymptotically by the Erdős-Stone-Shimonovich theorem. But for an even cycle, we have Ex and C2t. This is always upper bounded by something like n to the 1 plus 1 over t. Right. So this upper bound is true, but it's only known to be sharp in certain cases. For instance, it's sharp. Sharp just meaning in terms of order of magnitude. It's sharp if t is equal to 2, 3, or 5. And everything else is open. There's some general lower bounds, but they're not sharp, so I won't mention them. And then let me just mention the specific case due to Erdős, Renyi, and Sós, I think. Let's see. Yeah, Erdős, Renyi, Sós. That in the case of C4, not only do we know that the order of magnitude is n to the 3 halves, as required here, we know the constant. So the constant is a half. So it's 1 half n to the 3 halves. Actually, I can write a big O n there, but this is fine. Yeah, so that's good about that. Now let me mention that, so instead of starting with the complete graph as the base graph for these Turán problems, people have considered versions where instead of the complete graph, you start with some other ground graph. And a natural candidate is the bipartite graph, because if you're forbidding a bipartite graph, it's sort of natural to say instead of the complete graph, I start with a complete bipartite graph, and I ask how many edges I can take to forbid that graph. So this is the so-called Zerinkiewicz problem. It's tough to spell, so I'll write his name. I don't know if this is Polish or where it's from. So for instance, so in the classical extremal number, I write EXNF. So n, I mean the complete graph. But now, if I'm talking about some other base graph, I'll write the graph I'm talking about as the base graph as the first entry, and then the forbidden graph as the second one. So if we take as a base graph the complete bipartite graph with parts n half and n half, and we forbid C4, then it's known that we can improve this. We can improve this 1 half from the Erdős-Renyi-Sós result. This actually improves to 1 over 2 root 2 times n to the 3 halves. So it can be improved.
So what's the meaning of this notation? So
it means
that is the subgraph?
it means what is the largest subgraph of k n half n half, largest meaning most number of edges, so that we don't have a C4. So in general, I'll put some graph here, which is growing as a function of n. And then the question is how many edges we can have in that without the forbidden graph. So this is a variant that has been studied a lot, where instead of the complete graph, you have the complete bipartite graph. Yeah, the first, so EX and F, this is EX, K, and F under this new notation. Yeah. Okay, I just mentioned as a funny problem, which is actually still open, is if you replace K, N half, N half, if you say I have K, N half, N half, N half, so I take the complete tripartite graph, and I forbid C4, it's not known what the correct constant in front of n to the 3 halves is. So it's interesting. Okay, and I just mentioned some other settings in which some other base graph has been considered. So, for instance, hypercubes. One natural case is hypercubes. So, Erdős in particular started the problem where we take the base graph as the n-dimensional cube and forbid something. So in particular, the case of starting with the hypercube and forbidding C4, this is a famous problem of Erdős. And the question is to determine, so how many edges does the n-dimensional hypercube have? Well, it has 2 to the n vertices, and then each vertex has degree n. N, yeah. So it could in principle have n times 2 to the n edges, but the question is this little o n 2 to the n or not? So there's many open questions if you start with the hypercube as your base graph. This is known to be true, for instance, if you forbid some longer cycles, that it gets small, but in general it's tough. So here I would just mention that a lot of work has been done by this guy named David Offner. This topic. Okay, so what else people have studied? Instead of the hypercube, I can start with a random graph. Of course, now we have to be precise about what that means, but let me just write a random graph, Erdős random graph. And then there's many results using container method and these things, by Joži Balog and others. People have studied, instead of a random graph, I start with a planar graph, for instance. And there's a few results like this also, which have been done by, well, this was initiated by a guy named Doden, Christopher Doden. So people have considered some other starting graphs. If I have a hypercube, I have order n to n times 2 to the n edges. It's still order n times 2 to the n. It's a half. So little o, I mean, if I divide by this number, I tend to 0. Yeah. So the question in these hypercube questions, it's always, do I have a positive proportion of the edges, or do I have some fraction of the edges which tends to 0? And this is a tough question and open for most graphs, which are subgraphs of a hypercube. If you try to figure out their Turán number in the hypercube, it's open. Okay. So let me get on to the main topic. So now, just recently, a couple of years ago, a kind of a dual version of the Turán problem was introduced by Briggs and Cox. Christopher Cox is a student of Boris Buch. So here the idea is now, so we see that we can consider different starting graphs for the Turán problem. So now the question is somehow, what is the best starting graph to have if we want to make the Turán number small? So what is the best starting graph for forcing a copy of the graph if you take a few edges? So that's the question. So they defined, this is a slight abuse of a notation when I write it. They didn't write this notation, but it's so EXKF This is defined to be the supremum, and we'll see why it's supremum in a little bit, of the number of edges in a graph G such that G has n vertices and any k edge, well, let me write it this way, and Ex, so starting with G as the base graph of F, is strictly smaller than K. Okay. So this is what this is really saying is I start with a graph F and I look for the graph which is best at forcing a copy of F if I take K edges. Where's the M? There's no N. This is nonsense. Yeah, the N doesn't belong. Okay. Good.
Yeah.
Okay. Okay. Yeah. Okay. So this is the inverse Turán number. So one way to think about it, it's a little bit like if you were interested in Ramsey theory. Chalk my back. In Ramsey theory, there's this idea of like what is the size Ramsey number? So instead of looking at how many vertices I can take, so the complete graph forces the thing, you look at how many edges you can take, so that no matter how I two-color it, I get the copy of the thing. So it's kind of like a size Ramsey version for the Turán theory. Okay. So this is what we'll be interested in. So as a warm-up, what about Ex inverse Turán number of a star? Let's say a T star. What is the answer? Anyone have an idea? Let's write a K here instead of N, just to be consistent. So this is why I wrote a sup here, because suppose that K is at least T, right? And suppose that the graph I start with G is just a star. So it's a star with K edges, right? So if I take my base graph to be a star with K edges, then of course any T edge subgraph I take of this base graph has a star with T edges. So this always works. So I can take K as large as I want, right? So any star, as long as the star has at least K edges, will force a T star if I take K edges from it, where K is at least T. Right? So this number is infinity. Yep. Okay. Second strange case. Let's take a matching of size T. What about a matching? How many edges can I take in a base graph? So that no matter how I take K edges from that base graph, I get a matching of size T. Say infinity, yeah. Because I could take a size K matching. Okay. All right. So these two are strange examples, and what was proved by Briggs and Cox is actually these are the only strange examples. So these are the only way in which we end up with this inverse Turán number being infinite is if either we consider the star or we consider the matching. So I guess we can write it as a theorem of Briggs and Cox is that the inverse Turán number of graph F is finite if F is not equal to a star and it's not equal to a matching. So these are the two edge cases. Actually, they considered it a little bit more generally. They were looking at hypergraphs, and they said as long as F is not a sunflower, then this will be finite. Okay. So those are the two strange cases. So now some concrete things. So what about the inverse Turán number of the complete graph? So the question is which ground graph is best at forcing the complete graph if we take k edges from it? And again, if you think of sort of the size Ramsey number, there for forcing complete graphs, the answer is you should start with the complete graph. And indeed, for the inverse Turán number, the answer is again the complete graph. So what was proved by Briggs and Cox is that this number is equal to what you would get by considering the complete graph. Okay, so we have to calculate a little bit. What does that mean? So let me just write first attained by a complete graph. So what does that mean? So that means that if we so usually if we start with the complete graph, the Turán number of this thing is, as we calculated somewhere here, we see that starting with the complete graph, the Turán number is t minus 2 over t minus 1 times n squared with a half factor. So let's take k to be t minus 2, right? Yeah, t minus 2 over t minus 1. So if k is equal to this, let's say plus 1, then don't worry about the plus 1. Just care about the asymptotic for here. So this would mean that so if we had n vertices, then this is the largest number of edges we can take without a complete graph on t vertices. If I just solve this for n, I get n is equal to 2 times t minus 1 over t minus 2 times k, the whole thing square rooted. So in other words, what they proved is that Ex inverse k kt is equal to the complete graph on this many vertices. So it's equal to square root of 2 times t minus 1 over t minus 2 k, which is 2, which is just equal to, basically, if we're just squaring this, so we get t minus 1 over t minus 2 k, asymptotically, right? Because it's basically this squared over 2. So the inverse Turán number of a t-click is this. This is what's proved. Okay. So that's the starting case. Now, another natural setting is what if instead of a click we consider a path? Right? So the Erdős-Galai theorem. So in the classical Turán setting, there's a theorem of Erdős-Galai, which says that the extremal number, the classical extremal number, I'll write it with a kn, of the path of length k. This means k edges for me, always. So I always write pk, k edge path. This is k minus 1 over 2 times n. And the construction is just that I take n over k copies of a click, because a k click has no pk, because a pk has k edges, k plus 1 vertices. So I can take n over k copies of a k click, right? But if I just multiply this out, that's k times k minus 1. This gives me k minus 1 over 2 times n. Right? So this is the Erdős-Galai theorem. So now the question is which graphs are good at forcing a path? So Briggs and Cox proved that EX inverse K 3-edge path is equal to, well, it's equal to the, we should start with the complete graph. So it's equal to the complete graph. But on how many? Well, on k edges, so k squared over 2. So, right? So suppose we start with the complete graph on this many things. What's up? That's k choose 2. Yeah. So it says that if we want to, not k squared choose 2. I said k squared over 2, but it's roughly k choose 2. So they prove this. But they asked the question, what about P4? If we want to force P4, is it good to start with a complete graph to force P4, for instance? So we ask the question, what is EX inverse K P4? And the observation here is that the complete graph will not be optimal. And the reason is I will show you a better lower bound, a better construction than the complete graph. So imagine I start with a complete bipartite graph, part k of size k half and k half with all the edges. Now you can ask how big of a subgraph of this complete bipartite graph can we have without a P4? And well, one thing we could do is starting with a complete bipartite graph. We can take a star going downward and a star going upward like this in such a way that we exhaust all the vertices. Right? So this would be roughly k edges. And in fact, it was proved that if we start with a complete bipartite graph and we forbid a path of length k, then if the size of the bipartite graph is big enough, then the construction is always of this form, where we take two star-like things, we take two complete bipartite graphs in opposite directions. And this is always the best. So this was proved by Yarfash, Rousseau, Sharp, that the extremal number of this graph, the classical extremal number of the bipartite graph with size k half and k half, if k is large and you forbid a path, is that you should take two complete graphs in opposite directions. So for P4, the biggest complete bipartite graph we can take is just a K1T star. So the most number of edges we can get here is two stars in opposite directions. Okay. So here's a construction. So this is a lower bound. Now let's see how this compares to the alternative option. We could have started with some click, right? So instead of starting with this, we could have started with some n click. But we know that in a n click, if we forbid a path of length 4, the number of edges we can take. So k is how many edges we want to be able to take. We know that this is equal to 4 minus 1 over 2, so 3/2 times n. Right? So in other words, n is equal to 2/3 times k. So if we were to start with a complete graph, and we wanted the Turán number of the complete graph to be big enough to force a 4-path, we would have to take n to equal to 2/3 k. In other words, n choose 2 is at least 2/3 k squared over 2, which is so 2 over 9. Right, so this is 2/9, whereas here we have k-halves, so that's better. It's a 4th. 2/9 is smaller than a 4th. So this means that for P4, we know that we should not start with the complete graph if we want to force P4. And we see that a complete bipartite graph is better. So now what I want to do for you is I want to prove that there's nothing better than the complete bipartite graph, that indeed this is the graph that we should start with if we want every k edges to force a P4. Maybe before I start this proof, let me mention how this continues. So for P5, again, we proved that the complete graph is best to force a P5. And then for P6, it's interesting that Briggs and Cox, they thought that maybe the complete bipartite graph is best to force P6. But it turns out that no, to force P6, you should take the complete tripartite graph. Well, we don't know it, but we know that it's a lower bound if you take the complete tripartite graph, and it beats the bipartite graph. So it seems, and actually we conjecture, that to force the odd paths, the odd length paths, you should start with the complete graph. And to force the path P to T, you should start with the Turán graph with T parts. Seems to be the case. So this we conjecture, but we can only prove it for P4 and P5. So we proved that for P4, it's best to take the balanced bipartite graph. And we proved that for P5, it's best to take the complete graph. So let me discuss this proof of P4. Okay. So how would a proof like this start? We have to take a graph G, so that no matter how I take k edges from G, I don't have a copy of P4. So such that G has no P4 free subgraph of k edges. Right? So this is what we start with. Now, what do we know about G? So what we want to do is we want to show that the number of edges in G, we want to show it's at most k squared over 4. So we want to show that the number of edges in G is bounded by, let's just go for asymptotic, bounded by something like k squared over 4. So the first observation is about the number of vertices of G. So observation, the number of vertices of G, we can assume it's at most 2k. So there can't be a huge number of vertices relative to the number of edges. Okay, why is this? So suppose it was more. So let's look at the components of G, connected components. Right? So here's the connected components of G. And in each connected component, take a spanning tree of some kind. Okay. Now, if we look at such a spanning tree, we can find a big star forest. So here's a spanning tree, for instance. If I do a sort of breadth first search on the spanning tree, I can build a big star forest by taking all of the edges on half of the layers. So I either go to the first layer, third layer, fifth layer, and so on, or second layer, fourth layer, and so on. And in this way, I can get a big star forest. Big star forest meaning a star forest containing at least half the edges of the spanning tree. All right. So I have the star forest, but if I have a star forest, I don't have a path of length 4 in the star forest, because every star I only have paths of length 2, right? So in other words, what this is saying is if I have at least 2k vertices, I can take these spanning trees and I can find a star forest with at least or strictly bigger than half of the number of edges of each spanning tree. And of course, a star forest has no P4, so it means that the number of vertices has to be at most this. Okay, what would be the one exception would be if I could have isolated vertices, but of course there's no reason to take isolated vertices here, because isolated vertices don't help to force the PK. So as long as I assume my graph has no isolated vertices, then I see that I can assume that I have at most 2k vertices in my graph. Okay. But in fact, this 2 is not so important. All that matters is the constant times k for our proof, but this is what's true. Sort of the worst case scenario is we have a matching. Right? If the graph G was just a matching, we have no isolated vertices, but here, we have exactly 2k vertices that are used, k edges. Okay. Now, so how will we bound the edges? So the idea to bound the edges is to break the edges into different components. So start with the graph G and start by pulling out disjoint K4s one by one. So I take out a K4. And now I take a vertex disjoint K4. I take another vertex disjoint K4. And I do this until I can't take any more vertex disjoint K4s. And then I start taking K4 minus. So complete graph minus an edge. And I take another one. And I keep doing this until there's no more vertex disjoint K4 minuses. And now I take a C4, another C4, and so on until there's no more vertex disjoint C4s. Right? So I'll do this until I stop. And suppose that when I do this, I end up taking X K4s, and I take Y K4 minuses, and I take Z C4s. Okay. And let the union of the K4s, all the vertices above the K4s, let that set be X. Let the union of the K4 minuses be Y. The union of the C4s be Z. And let S be the remaining vertices. Okay. So now I want to start bounding the edges. So first, what can we say about the number of edges in the graph induced on X? Well, we can't say very much. Maybe we have all the edges on the graph induced in X. So we have little x copies of K4. So we could, in principle, have 4x choose 2 edges. So totally trivial bound. Little x K4s, we can have all the edges among these vertices, so 4x choose 2. What about the edges on the Y part, on the K4 minuses? Now, the way we did this was that we took all the K4s first, So we know that on the K4 minus vertices, we don't have any K4. So we can apply Turán's theorem. And Turán's theorem tells us that, well, if we don't have a K4, then we have at most, Turán graph, so 3-part that graph. So there's 4y vertices over 3, quantity squared times 3 is what the Turán's theorem gives. And this is equal to 16 over 3y squared. Okay. What about the edges on Z? Okay. So now on Z, we know we don't have K4 minus. Okay. But what's special about K4 minus? K4 minus is such that if we remove an edge, we reduce the chromatic number by 1. So this is this theorem of Shimonovich, which I mentioned that the Erdős-Stone-Shimonovich theorem is tight if we have a graph where removing an edge reduces the chromatic number by 1. So we know that K4 minus behaves exactly like a triangle, right? So again, we can bound this simply by saying we have 4z vertices over 2 quantity squared, which is 4z squared by Shimonovich's color critical theorem. Okay. And finally, let us look at S, a set of remaining vertices. So E of the remaining set. Well, now we've gotten rid of all there's no C4 on the set S. So we can just write very simply big O k to the 3/2. Why can I write k here instead of the number of vertices? Well, because I proved this thing about the spanning trees that the number of vertices is bounded by 2k. So I can write k to the 3/2 bound on the number of edges here. Okay. So that's a bound on all the edges which are contained in one of these parts. Now I have to bound all the edges which are crossing the parts somehow. So first let's look at xy. I see that time is going fast, so I won't do everything, but I'll give some examples. So how many edges can we have between x and y? Well, I claim that we can have at most 14 xy, little x, little y edges between x, y. And what is the reason? Suppose I had more than this number of edges, then there'd be some k4 and some k4 minus, which had 15 edges between them. So otherwise, we would have a k4 and a k4 minus with at least 15 edges between them. Right? That's what it would mean to have more than this number of edges between part x and part y. But suppose this is the case. Well, let's just draw a picture. Let me use red to denote that we don't take the edge. So what do we have? Maybe we don't take this edge. But then take a look. If we take this vertex, this vertex, this vertex, and this vertex, these 4 vertices form a K4. And if we take this vertex, this vertex, this vertex, and this vertex, these 4 vertices form a K4. So what we would have is on these 8 vertices, we would have 2 copies of K4, which means that we were not being optimal with x, that we could have taken 2 K4s instead. So we don't have this. So this bound holds, and the rest of the cases will be similar to this, that we'll get a contradiction about the maximality of x or y or z. So next case, x and z, we want to bound by 12xz. So what would it mean to have more than 12xz? It would mean that we have a K4 and we have a C4 with at least 13 edges between them. Right? So let's look at this. So if this were true, what does it mean? So first off, could it be that we have a vertex here? What is the point here? yeah, so let's look at these 13 edges. And there's cases. So we can either have, how can the degrees of these vertices be in terms of going to the left? We could have 4, 4, 4, 1, right? Three copies of a degree 4 vertex to the left and 1 copy of degree 1. We can have 4, 3, 3, 3. Or we could have 4, 3, 4, 4, 3, 2. Right? These are the possibilities. Okay. So first let's look at 4, 4, 4, 1. So imagine we have 4, 4, 4, 1. So here's the vertex of degree 1 over here. And the point is that, well, this one is adjacent to, say, one of the vertices of the K4. And what I will do is take this vertex and its two neighbors in the C4, and this vertex. And these four vertices together form a K4. Because this is 4, 4. Yeah. So with the rest, I get a so this vertex combined with its two neighbors plus its neighbor in the K4 yields a copy of K4. Now let me look at the remaining vertices. This one, this one, this one, this one. Well, these are also a K4. So contradiction again. So this case is done. 4, 3, 3, 3. So, okay, let's see what's the case. Well, what's up? So, let's see. So what I do is I take this vertex. Maybe you're right. Maybe it's a K4 minus. So I take this vertex and its two neighbors. Right. So K4 minus and K4, but it's still a contradiction. Yep. Okay, so next case with the threes, it's a similar deal that, I mean, I definitely have two adjacent vertices of degree 3. And these two vertices of degree 3 to the left both have two common neighbors at least. So if I take this one, and these are the two common neighbors, this is a K4. And then these two, this one is the neighbor of either this or this, okay? So it's going to miss one. But nonetheless, if I take this vertex, this one, and this one, I will get a K4 minus. So again, I will get a K4 and a K4 minus. And the next case, if I have a 3, 2, again, the reasoning is sort of similar. If the 3 and the 2 are consecutive, I could take this vertex. There will be at least one common neighbor of these two, so I'll take that one. And then I can take one more vertex of the degree 3 one, or rather of the degree 2 one. And these will form a K4 minus. And again, I can take the remaining ones. So this is how this kind of thing.
They are opposites, 3 and 2.
Okay, so if they're opposite, so there's a good case if they're opposite and a bad case. Let's see. So if they're opposite and they share two common neighbors, then again it's easy. So let's look at the bad case where they're opposite and they don't share two common neighbors. So this is what we have to look at. So we have 3, 2, 4, 4. They definitely share one common neighbor. And what can we do? Well, actually, this is not so bad, right? Because there's one other neighbor of the 2-degree vertex, which is not the neighbor of the 3-degree vertex, but nonetheless, these 4 vertices form a K4 minus. No, they don't. That's good. Let's see. Right? It's not good. Let's see what we do. No, here we do something else. 2, 4 pair, you say? So take the 2 neighbors of the 2 pair. These are also neighbors of the 4 pair. Yes? So that makes a K4. And now we have to take the 4 and 3. But you're right. This will be a K4 minus. Thank you. Yeah, so. Okay, so that's how this game goes. Again, for time reasons, I will not show, but then we have EX with E, XZ. This is most 10 YZ. They're the same sort of thing.
You just did XZ, so now YZ.
YZ, thanks. Yep. YZ. Yep. Okay, so that's the first part. And the second observation is now, this is a K4, or a K4 minus, or a C4, I don't care what. And here is S. And I want to bound how many edges I can have between this K4, K4 minus, C4, and S. Now, first I want to bound how many vertices I can have in here, which are neighbors of some vertex from here. And the way I can do that is that I can have at most K minus 6x minus 5y minus 4z plus 6 neighbors in S, because if I had this many neighbors in S from one of the K4, K4 minus C4, I could build a star forest using those vertices in S and this many edges. So I could find this many edges in a star forest with this object over here. And then all of the remaining K4s, K4 minus C4, I can take all the edges from, and I don't have a P4 in any of those. So I'm going to add to it 6x plus 5y plus 4z, with the exception of the 6, which might have been involved with this one, which I'm considering right here. But it doesn't matter because I added a 6 here. Okay. So in other words, if I had too many neighbors from one of these objects, I can build a star forest off that object to all of the neighbors over here, and then take all of the remaining K4s, K4 minus C4s. And together the number of edges will be at least K. And that graph with K edges, which I get, will not have a P4. So that will be a contradiction. So the lemma here is that for any of these K4, K4 minus, C4 I take, I have at most this many neighboring vertices in S. Okay. Now, that implies in particular that the number of edges from, say, X to S, well, everything in S, I have at most this many things in S, which are neighbors of each thing in capital X, but then there can be four vertices for that. So I have to write, this is at most 4 times K minus 6x minus 5y minus 4z plus 6. Okay, so here's an upper bound on that. Now, the number of edges from Y to S, again, from each object from Y, from each K4 minus, we have at most this many neighboring vertices in S. But for each neighboring vertex in S, we don't have all the edges back, because suppose we did. Suppose here we have K4 minus, and suppose here we have a vertex with all of the neighbors back. Well, this is a contradiction because we can find now a K4. So we can write, instead of a 4, we can write a 3. So this is bounded by 3 times K minus 6x minus 5y minus 4z plus 6. Yep. Yes, thank you. 4x, 3y. Yep. And finally, by the same reasoning, from z to s, we can now bound by 2 times z, k minus 6x minus 5y minus 4z plus 6. By the same thing, if we have too many edges back, then we generate a K4 minus. Okay. So what is the point? So we now have estimates on all of the edges. If we add these all up, which I won't do, but if we add these all up, we will upper bound by k squared over 4 plus big O k to the 3 halves. So that's that. And so let me just mention in my remaining minute that, so that's for P4. For P5, actually, we have a pretty different proof, but surprisingly, the same idea doesn't work. But I won't go into details. For KST, surprisingly, we're able to determine this number exactly. I mean, not exactly, but asymptotically. So we're able to prove that EX inverse KST is equal to n to the 1 plus 1 over s. This is for s less than t. So this is kind of weird because in the Turán problem we don't have a correct number here. But for inverse Turán, we can figure this out for every s and t. So in particular, if s equals t equals 2, and this deals with C4, which was an open problem of Cox and Briggs in their paper. And yeah, so, and finally we worked also on C4. We had slightly better bounds. So what we were able to prove is that 2 root 2 over 3 root 3 k to the 3 halves plus that EX minus so this is what we can prove about C4. So there's still a gap. I mean, so we answered a question of Briggs and Cox. They weren't sure about the order of magnitude. We proved that the order of magnitude is k to the 3 halves, but we don't know the constant here. And actually, we write in the paper, we conjecture that this crazy number on the left is the right answer. It's 2 root 2 over 3 root 3. So, yeah. Okay. So I guess I'm out of time, so I stop.
The maximum number of K4 minus. Was this technique known? Or?
I think it's pretty new. Certainly something like this has been done somewhere, I'm sure. But
yeah.
For very different problems.
It's neat. That requires lots of computations, but is the optimizing this function, was it a difficult task or is it an easy exercise?
Well, if you guess the right answer, then it's easy to check on Wolfram alpha that it works. So not so hard.
Where does it fail for next step? Like P6?
Pushing the method further, but it's somehow a very different idea is used for P5. So some new idea is needed for P6. But it seems like for P6, the answer should be a complete tripartite graph. Because this beats the clique, this beats the complete bipartite graph. So it seems like a complete tripartite graph is best for forcing P6. But even the Turán number of pk in general for a complete tripartite graph is not known.
Can you get the bound for the K3 plus 1 edge?
K3 plus what?
Another edge.
K triangle plus an edge. I don't know. I haven't tried. Seems maybe it's possible.
So what happens if you take the inverse transformation of a three-chromatic graph? Is it known or?
It's known that the answer is linear. And the reason is that there's sort of a, let me see if I get it right, that in general, if we know that, so Briggs and Cox prove something like if the extremal number is upper bounded by big O n to the beta, then we can lower bound the inverse Turán number by something like k to the 3 minus beta. So I guess beta is bigger than 1. So you say if we have a three-chromatic graph, beta is 2 because of Erdős-Stone-Simonovich. So we know that, actually no, this doesn't really say very much, does it?
Yeah.
Okay, no, so,
At least linear.
okay, doesn't say very much.
The above implies below?
This implication is proved by Briggs and Cox.
Then how about Cox?
That if you have upper bounds on the extremal number, you have lower bounds on the inverse Turán number. Converse is not exactly true, but there's some, you should look at the paper. There is a kind of a converse, but it's weaker.
Do you suspect that the inverse Turán number of a graph with chromatic number at least 3 should be given by some clique?
I think so. That should be true. It would also be interesting to try to figure this out, like in the case where you have these color critical graphs. So,
Yeah.
So Briggs and Cox, they settled it for cliques. So maybe the next step is instead of cliques to have color critical, at least 3 chromatic graphs.
Any other questions? Okay, you can add less than speaker. Okay.